Then is about the graph of function, like especially the graph of rational function. To do the sketch the graph of functions, what we are focusing first is the domain. Right? The domain, we say a couple of things to be important. The first one is domain. Domain is denominator not equal 0 for the rational function. The positive and negative one will make the denominator to be 0, so excluding those values out. From negative infinity to negative 1, union negative 1 to 1. Also union 1 to infinity will be 3 pieces of our domain. Our range we don't know yet, since the function is not clear. That the next thing is vertical and horizontal asymptotes. Right, the vertical asymptote is we check if a function could be simplified. Well, we have the term x plus 1 on the denominator also, so it can be simplified or still could be reduced. Right, the top has the term of x plus 1, bottom has the term of x plus 1. We'll leave 1 left over. So the expression is same as 1 over x minus 1. The extra condition is x cannot be negative 1 as was originally in the denominator. Right, so the function graph will be similar as this one. Our vertical asymptote is at x equal 1 for the denominator. Our horizontal asymptote, since the top has a power 0, bottom has power 1 of the polynomial, right, we have y equals 0 as the horizontal asymptotes. Usually for the rational expression of rational expression, right? We have polynomials on top and bottom. The leading term is the a to the n, x to the nth power, x to the n power of the coefficient a m and b m. Right, so 3 cases. If n is bigger than m, there's no such horizontal asymptote that exists. If they are equal, the horizontal asymptote will be the ratio of the quotient. Right? The ratio of their coefficient, not quotient. If n is smaller than m, we'll have y equals 0 as the horizontal asymptotes. Right? That only holds for the polynomials on each part of the fraction. Right, in our case, we have x to the power 1. They have constant on the top, which is to the power 0, which is x to the power 0. Right? That is a linear term and a constant. Therefore, top power is smaller than bottom power. We have horizontal asymptote to be y equals 0. Right, so a couple other things may be important as the whichever thing, the x-intercept, y-intercept. Let the f of x to be 0, that's the y-intercept. And that's the x-intercept. But that's no solution, right? 1 over x minus 1 cannot be 0, since the numerator cannot be 0. Right? Our y-intercept is f of 0, which we could substitute into the simpler function. 1 over 0 minus 1, that's negative 1. Right, so a couple of things are clear. That doesn't have the x-intercept, have the vertical asymptote at x equal 1. Right, just label them clearly to see what we have. Right? And we have a rational expression is pretty clear. That will be two pieces. Right, when we have the 0, negative 1 as the y-intercept, then the graph will be this. Right? Since we have the horizontal asymptote at y equals 0, and the other piece will be going the other way. You can use substitute more points in, right? Such as f of 2 is what, f of 3 is what, or f of negative 2 gives us what value, f of negative 3, or so on, right? 0.5, 1.5. Substitute in, we can see the y values, such these will be a function. And the extra condition is x cannot be negative 1. So for x to be negative 1, we just dig a hole on our function. That is the not continuous part, discontinuity. Just a hole over there. Right, so that is this rational function. And a couple other things, right? Like what we see. For which value is decreasing, for which value it is increasing, and also about the concavity of the function will be what we will discuss in our semester here in our course. And to sketch a relatively more clear graph, right? How do I know this is fastly going down? How do I know this one goes not that down, it goes down not that fast? How do I know this one goes down? But without aid of extra points, we should be able to know them with the technique we learned from our semester, our course. So to draw not that the roughly graph, we will draw a relatively more clear or a more detailed graph, right? That is our purpose in our semester here also, one of the purpose. Also a rational expression function, x squared minus 4x minus 5, still the first thing, over x minus 5, the domain. The denominator cannot be 0, that x cannot be 5, right? 5 will be digging out from the real number system. Right? Only the 5 is being digging out, that everything before, everything after will be good. That is why we write it. Of course, could be other ways to write it, but just consisting one will be good enough. Right? Then to find vertical or horizontal asymptote is to simplify our f of x. The numerator is able to simplify, right? That's the square term, which we can factor as x and x. Logging for two number have product of -5, have sum of -4, that's 1 and 5. positive 1, negative 5 will give us product as negative 5 and sum as negative 4. Which luckily that we have x minus 5 as the term on the denominator, so we are able to cancel out the x minus 5 to leave x plus 1 at the end with a extra condition that x cannot be 5. So these expressions are same, the extra condition is involving there, make them exactly same. So f of x is actually the line of x plus 1. Then there are no other things we need to do, like we don't need to worry about the vertical horizontal asymptotes since we have a linear equation here. Right, then 2 points can draw a graph. When x is 0, y is 1, when x is 1, y is 2, that we have a straight line, but also the x equal 5 should be digging out. Right. It's supposed to be 6 when x plus 1 is the expression, but x cannot be 5, so even the value that we can see is as x approaches to 5, f of x, which is the expression of x plus 1, approaches to 6. Right? It is on the path of x plus 1 that it's supposed to be 6, but in this case the 5 is digging out, but when x is approaches to 5, the f of x is approaches to 6. Right, so this value actually is not defined, we digged out because the nature of the original function, but when x is approaching 5, the f of x is approaches to 5 plus 1, which is 6. Right, so that is the idea that even it is digging out, or even it is undefined, but it doesn't matter that along the path of the function, as the x value arbitrarily approaches to the x, to the 5 in this case, our y value is approaches to 6. That will be what we discussed in the first chapter of the first section, which is called the limit. That is very informal definition of the limit, that as x arbitrarily approaches to such value, what is the y value it approaches to? Arbitrarily means from the left and from the right along the path of f of x, the value of the y is approaches to some other value. Or maybe in this case approaches to 6. Since we get function is defined as x plus 1 after simplifying it, but it is approaching, right? So even though it's not defined, it can be approaches to this value, and this idea is called limit, right? The limit. Right, so that's from the graph of rational functions we discussed. Then the trigonometry. Well, for a xy plane that maybe we'll not leave it in the first quadrant, maybe we can leave it's in the second quadrant. We have the original, the first initial side is always the positive x-axis. The terminal side of the angle is what we have, right, to identify the angle, and forms together from positive x-axis to the terminal side is the length of the angle, right? And what we do is get a point on the terminal side and draw the vertical line down to x-axis to form a right triangle. Then we have the opposite side, adjacent side, and the hypotenuse side of the right triangle, right? Because we have the angle here that its reference angle is the reference angle is the angle that x-axis and the terminal side formed, which is the acute angle that it forms. But the true angle is this theta, that we have a right triangle formed by the reference angle, and the opposite side of the reference angle, adjacent side, and hypotenuse side of the reference angle have the same value as the original theta. Right, so define is this way. The sine of theta is the opposite of hypotenuse. And the cosine of theta is adjacent of hypotenuse, and tangent theta is opposite of adjacent. Like when we see the slope of a line is actually the difference of y over the difference of x, which is the tangent value of the quotient or of the angle. Right, so that is tangent. And three other values are cosecant, which is hypotenuse over opposite, and the cosecant is reciprocal of sine. Secant is the reciprocal of cosine, that is hypotenuse over adjacent, and the cotangent is adjacent over opposite. Right, so that's 6 trigonometric functions of theta: sine, cosine, tangent, cosecant, secant, and the cotangent, which that's what they are. And there are a lot of formulas. In summary, we have quotient relationship, reciprocals, and sum of squares, right, which is called what? Pythagoras relationship, which can be summarized as a picture for the sine, cosine, tangent, cotangent, secant, cosecant one in the middle. That's an angle of theta. The diagram here can help us to memorize all the majority of the relationship. First of all, the diagonal. Each diagonal, right? We have sine and cosecant, secant and cosine, tangent and cotangent. The diagonals are in the relationship called the reciprocal, which cosine is 1 over secant, secant is 1 over cosine, sine is 1 over cosecant, cosecant is 1 over sine, tangent is the reciprocal of cotangent, cotangent is 1 over tangent. Right, that we have 1 in the middle. The next relationship is their edge. Their edge. What it means, majority most classic one is tangent is sine over cosine. Which any arbitrary point here, that value is the next one divided by second from the same side. Which tangent is sine over cosine, tangent is also equal secant over cosecant. Right, secant over cosecant. When you view in this case, secant over cosecant, when they divide it to each other, they will be become opposite of adjacent. Also, not only tangent it works. Cotangent is cosine over sine, is cosecant over secant. Cosecant over cotangent is secant. Right. Cosecant over cotangent is secant. Cotangent over cosecant is cosine. Right? Cosine is cotangent over cosecant. Also, cosine is sine over tangent. So that much different relationship. That could be explained by the edges. Right? The edges connected to the next one over the same side, the second, over the one that is on the second on the same side. Right? In other words. Right? That can be 6 points on that, which we have one direction, the other direction. That's in total 12 different quotients can be found. Right. And the third one is the Pythagorean relationship. Such one, classic one is sine square of theta plus cosine square of theta. We write square here, not on the end, because well, it is a little more confusing to write sine theta square. We don't know if the square belongs to theta or belongs to the sine. So for the power of trigonometric function, we always put it in the middle of the angle and the trig function. Right, and that is equal. Right, that's most classic one, that the sum square of two terms gives the third one. Right, and the two other things we may use them, that 1 plus the square of tangent will give us the square of secant. 1 plus the cotangent square will give us the cosecant square. We can see that, well, there is a open side on the parenthesis, which shows that the sum square of the two terms here equals the square of the third. The sum square of tangent and 1 will equal to the secant square. The sum square of 1 and cotangent will equal to the cosecant. Right, tangent square plus 1 equal to the secant square, and so on. That is the trigonometric. Well, this thing we'll use that in our course here. This thing, sometimes we're going to use it to simplify, but if you are in calculus 2, right, if you move on to calculus 2, like integration of calculus, you will use the trigonometric function, and the basic ones like these should be also used. Well, for piecewise functions, a piecewise function is the function cut into pieces. Each piece may be polynomial, may be some other type of function, doesn't matter what they are, but that's how it's defined. Right, the function is defined as x squared plus 1 when x to be positive or 0. It's defined as x minus 1 when x is less than 0. Right, so evaluate for different x value, we need to check which piece are actually we use. Right, so f of -1, such -1 is in the piece that x is less than 0. So we use the second piece to evaluate in -1 minus 1 is -2. F of 0, the 0 falls in the first piece, x greater than or equal 0. So we use the first piece to evaluate it. Substitute the 0 into the function. Is 1. Right. And f of 1, that will be also falls in the first piece, that's 1 squared plus 1, that is 2. Which, if we want to sketch the curve, that for x is less than 0, that is a straight line. For x is bigger than or equal 0, that is a parabola. We get 0 at 1, 1 at 2 of that parabola. It's defined over here. But the line x minus 1, -1 is -2. This point, but it's defined all the way to x is less than 0. So we need to check an extra thing is as x approaches 1, x is approaching to 0, but a little less, right? That notation raise the negative sign means it approaches to 0, but a little less than 0. It's still following the term of x is less than 0. F of x approaches to 0 minus 1, which a little less or a little more doesn't matter, right? That is still 0 minus 1, it's -1. So when x is a little smaller than 0, f of x will be approached to some value is -1. So -1 is digging a hole, and that is a line. Right, so that is the sketch of f of x in this case. The key thing for piecewise function is be clear which piece we are doing. Right, to evaluate the function when x is -1, 2, 3, 4, or 5. Right, so -1 is in the case that x is smaller than 2, right? The function, you can read that, is defined into 3 different pieces, 4 different domains. When x is smaller than 2, that's first piece. When x is bigger than 2 or smaller than or equal to 4, that's 7, second piece. When x is bigger than 4, that's third piece. Right? So when x is -1, that's 4 in the first piece. -1 cubic is -1 still, times 2 is -2 minus 1 is -3. And especially when we check the f of 2, that we didn't have the piece, right? When x is smaller than 2, that's first piece. When x is bigger than 2, or something else, that's second piece. But at x equal 2, it actually doesn't have the definition inside our function. Right, so we can say it's undefined. Right, the f of 2 actually in our case is undefined. F of 3. F of 3 in our case, which is in between 2 and 4, that's clearly is 7. And to check f of 4, we have f of 4 has the value x equal 4 defined in the second piece. That's the value, no matter what the x is, that is the value of 7. Right, so any value between 2 and 4, the y value remains constant as the horizontal line at 7. Then the last one, f of 5. Is to substitute 5 into the function, which 5 is bigger than 4, the third piece, 2 times 5 minus 3. 10 minus 3 is 7. Well, just luckily to get same number but not necessary. If you get 8 in, that will be different. But again, our key thing is to know which one it is. And some other thing we'll see is exponential function. Such that f of x equals a to the x. That condition is a need to be bigger than 0 but not equal 1. Right, to sketch the graph. When a is bigger than 1, that is the case that we'll get an increasing function. Point will pass in at 0, 1, since anything raised to the 0 is 1, if that is positive, not 1. And it will have a horizontal asymptote at y equals 0. On the left. On the right, it's going to infinity, such as like 2 to the x power will be increasing more and more for x to be larger and larger. We've approached to 0, but still positive on the left side. Right, if you put 2 to the -5 power, that will be 1/32, which will be small. If you put 2 to the -10, it will be already a 0.001, a little bit bigger than 0.001. But it will approach to 0, but still positive on the left. When a is between 0 and 1, that's the other other side, flipped. That still past the 0.01, it will go infinity on the left, and we'll have a horizontal asymptote on the right. as x approaches to infinity, our y will approach to 0. And some property that when multiply, that gives the sum. When you divide, of course, will give quotient, and power to power will be product. Some property of exponential function is this. And when we see the logarithmic function, logarithmic was defined as inverse function of exponential. So the condition is saying we need to be greater than 0, not equal 1, that we can find the log. For it to be bigger than 1, we have that function, we have horizontal, vertical asymptote actually. At x equals 0, we have 0.10, and domain is positive, x to be positive, range is all real number. Domain before was all real number, but range is y to be greater than 0 for the exponential function. For logarithmic, domain is x to be greater than 0, range is all real number it can take. Similarly, for the in between 0 and 1, that logarithmic function is upside down. 1, 0 is the point it passes, and the horizontal asymptote happens to on the top. Sorry, it's vertical asymptote happen to from the top as x equals 0. Approaching to it, never get it, goes to infinity. And domain and range also that. Some other property for log. Product becomes summation. Quotient a base of u over v will become the difference of the same base. And the third one is exponent become coefficient of the log. And that's three very important property. Will change a very tricky expression into the log expression format, and will make it do a little easier. We will see what it means later. But that three formulas, product, quotient, and exponent. Product will become sums, quotient will become difference, exponent will become coefficient, is also a very important property of logarithmic functions. So that is the review of precalculus, what majority thing we need to know. Maybe some other things we still also need to be reminded that we will see when we go into the chapters. So next we will move on to our chapter 2. The first section will be section 2.2. The chapter 2 is about the limit. The section 2.2 is using some aid to find limit. I will see.